Hello. Yeah. So today we'll discuss. This is week 9 live discussion session, and in this week we'll discuss in detail the theory of Rao's polymers. We'll discuss some question from this section, uh, which will be helpful to solve the assignment in the coming week. Okay. Let's start with first problem. So first problem is. Uh, So there are a couple of statements given in the option. You have to identify which of these statements are correct. So true, false type we may say. There are four statements. Rao's model gives correct diffusivity. B. Rao's model is based on bead spring model. Option C. Rao's model includes the effect of thermal fluctuations, and D. Rao's model includes effect of hydrodynamic interaction. So these are the four statements you're given here, and you have to identify which of these statements are true and which are false. Now let us discuss briefly what is Rao's model. So basically Rao's model is extension of bead spring model of polymer. So suppose these are the bead connected by springs, which is representing the polymer. Now suppose this is the nth bead, this is n minus 1, this is n plus 1. Now the spring energy of nth bead associated with the nth bead is like U spring is half k Rn plus 1 minus Rn whole square. This is due to the spring here, this spring, and half k Rn minus Rn minus 1 whole square. These are all vectors, and this is due to this spring. So this is the total energy acting on this nth particle from the both side of the because it has spring on the both side, so there will be energy associated with each of the spring, and I am writing down two term of the form half k x square, which is the form of spring energy, and so this will give the energy associated with the nth bead in the polymer. Now so basically when I am writing the equation of motion in this scenario, there I am writing equation of motion of bead spring model essentially with some extension which includes the thermal fluctuation. We will come slowly to that. So we got U spring, then force is given by F of Rn is minus del U del Rn. Now if you do this from the first one, you will get, so because there is a minus sign, so it will be plus k of R plus term, and in the next one it will be minus. So from both these squared term, there will be minus 2 Rn, and there will be this term Rn plus 1, Rn minus 1 minus 2 Rn. So this is the force acting on the nth beat. Now if we want to write down the equation of motion, that will be like mx double dot is minus psi x dot plus random force thermal fluctuation f of RT minus del u del x, the potential due to the force due to the potential. Now this term is 0 here, and we'll take this term to the left hand side, and then we'll get dx dt equal to minus 1 by xi del u del x plus f of r t by xi. We'll write down the last f of r minus by xi as v of r, some kind of velocity, del u del x plus v of r. So you can see that essentially this is an extension of bead spring model which accounts for the thermal fluctuation. So this is correct and this is correct. Now correct diffusivity it cannot predict, because it predicts, we'll see in the next section that it predicts diffusivity which is of the goes like d proportional to 1 by n, but which is not the exactly correct relation, but we'll see that in detail in the next section. But this is not correct, it cannot predict diffusivity, and the Rao's model includes effect of hydrodynamic interaction. This is also not correct, because we haven't included any hydrodynamic interaction term in this case while writing down the equation of motion, whereas the hydrodynamic interaction will be taken into account when we do the Zim model, which is the next section. So this is also not correct. We'll go into the details of this equation of motion more. So now the property of this VRT is essentially like random force, which is average of V of RT is 0 and T V of RT prime is like 2 diffusion constant delta T minus T prime. Now so we got the equation something like this here, which is in terms of our own variable r will look like d of r in dt is, now del u del Rn, the force we have already derived, and that will be k by xi Rn plus 1 plus Rn minus 1 minus 2 Rn plus V of Rt. And the boundary spring is slightly different, because it has associated only one spring, because this is suppose the boundary bead, it will have only one spring attached, whereas all the intermediate bead will have two spring attached. So the equation of motion of the boundary beads will be somewhat sort of will look a little bit different. Suppose dr0 dt, it will have k by xi r0 minus r1, thermal fluctuation term is same, V of RT and d of r in capital M. Thinking there are capital N number of total beats and n minus 1 number of springs. K by xi Rn minus 1 and V of RT. So this is the overall equation of motion, set of equation of motion that we have to analyze. Now in these two equations, say this is equation 1, 2 and 3. In 2 and 3 this looks like a forward or backward difference. So this is also essentially same as the first derivative, whereas the equation number 1, this is like a second derivative term. So if we transform this into some kind of partial differential equation, then it will be d of r and dt equal to k by xi del 2 r del n 2 plus v of rt. We have written this term, this whole term, as del 2a, something like this term as del 2a. And we will write down this term as first derivative. These are the first derivative term. So there will be two more equations. So let's write down this as 1 prime. The 2 prime will be dr0 dt k by xi the partial derivative of r with respect to n at n is equal to 0, 0 and 3 prime will be d of r n dt k by xi del n at n is equal to capital N v of r t. So these are the equations. Now let us discuss one more question, the next question in the assignment. Like, what is the boundary condition? Question number 2. The boundary condition is what? Del 2 r del n2 is 0. Option B, rn minus r0 is equal to re. Option C, rn minus r0 whole square ensemble average is re square average, re square, and option D is del r del n equal to 0. Now these are the options, but del r del n will be 0 only in the, so more appropriately saying these are 0 at n is equal to 0 and n. So this is the correct option because these n's are perfectly free end. So partial derivatives of r with respect to n at this particular two position, n is equal to 0 and capital N, there it will be 0. So these are the boundary condition of this system. So this is due to so this is due to the free end approximation. The ends, the two sides of the chain, endpoints of the chain are free to move anywhere. There is no restriction on this. So the partial derivative with respect to n is 0 at n is equal to 0 and capital N, which are the boundary. So this is the chain. This is n is equal to 0. This is n is equal to capital N. These are the two boundaries. Okay. Let us move forward with this. The question number 3. Question number 3 is the basis function used. The basis function used in the Rouse model, now the option phi p in is 2 by capital N cos p pi n by capital N. Option B, phi p n is 1 by n cos 2p pi small n by capital N. Option C, phi p n equal to 1 by n sin p pi n by capital N. Option D, phi p n equal to 1 by n cos p pi small n by capital N. So this is the option. So we got the equation like in the previous page. We got the equation like d r n dt is k by psi del 2r del n2 plus v of r in comma t. This is the equation we got. Now we consider the Fourier transform variable of r. So we consider some xp, which is Fourier transform variable of r, defined like dn phi p n defined like this, and this phi p n is the basis function we want to find out. So for which basis function this will work. So now if we calculate this quantity xi p dxp dt, we calculate, it will give xi p ddt of this whole term 0 to n dn phi p n r n comma t. Now we can move the ddt inside because the integration is over n. So outside xi p will be as it is, and 0 to n dn phi p n partial derivative, it will be partial because r is a function of n and t both, but we are taking a derivative with respect to time only, so it is partial derivative. Now notice that this particular quantity is already known to us. This is what? This is k by xi del 2r del n2 plus f r by z. So if you put that inside these, if you replace this particular quantity with this quantity, this whole quantity, and then if you integrate by parts, you will get the equation which is of the form xi p dxp dt is equal to minus kp xp, which is a fp. So overall this is a ordinary differential equation, and from the intermediate step we will get one relation like del 2 phi p n del n2 is minus a square phi p n, where a is, if you don't remember this step, please see lecture number 2 or 3. It is derived in detail. I am just keeping some of the steps here, something like this. Now this equation we need to solve to get the form of phi p n. So this is fairly simple to solve, and the solution will be of the form phi p n will be alpha, some constant, cos of a n plus beta, some again constant again, sin of a n. Now we have the boundary condition. So del phi p n del n will be 0 at n is equal to 0. So this gives me beta is equal to 0, and del phi p n del n is equal to 0 at n is equal to capital N, which gives me sine of a capital N is 0, which gives a is equal to p pi by capital N. So the basis function phi p n is alpha cos p pi small n by capital N. Now choose alpha, is choice alpha normalization constant 1 by n. So phi p n will be 1 by n cosine of p pi. So we have got the form of phi p n. So let me repeat once more what we have done here. So we got this equation from bitstring model using our idea of writing Brownian dynamics of a particle. From that we have defined a new variable xp, which is some transform variable of r, and in the basis function for the transformation is phi p n. We need to find out the basis function used in Gauss model. So we have taken psi p xp, psi p dt of xp. We explicitly wrote down the term and we got this equation, ordinary differential equation, in the psi p space, not in the r space. So we have transformed the variable. Now we have all the equation in the psi p xp space. So from the intermediate terms we get this equation of phi p n, which takes us to the solution. Phi p n is 1 by n cos p pi n by capital N. So the correct option is, in this case, the last option is here, this one. Let us see the next question. Question number 4. True false type. True false type question. Question is, center of mass of a polymer chain can be outside the polymer chain. True false type question. So this is essentially true because suppose your polymer chain looks something like this. So the center of mass can lie anywhere, like this can be center of mass, or somewhere here. This can be a center of mass in midpoint, but it is not necessarily that it is situated but on exactly on the polymer chain. It can be somewhere outside the polymer chain also. So one good example of this, if you want to calculate the position of center of mass of a circular ring, this is exactly just this point, the center of the circle. So this is outside the actual object. So center of mass is not situated on the object, it is on the center of the circle. So you want to calculate this. Suppose this is a circular ring which is of mass n. You want to calculate center of mass. So there is no doubt the center of mass is, so mass here, mass is acting through the center of the circle, so which is outside the ring. So it is possible that in the case of polymer also, the center of mass can lie outside the polymer chain. It is not necessary that it will always lie on the polymer chain, on the backbone or something like that. Okay, so this is a small question. Then let's move to next question, question number 5. In the Let us do this question first. For the continuous analog of the bit spring model, Kp is given by option A 2k p square pi square by capital M, option B 3k p square pi square by capital M, option C 2k p square pi square by 3m, and option D is k p square pi square by m. So if you remember in the last equation we got some, in the last question we got some equation which is of the form xi p ddt of xp is minus kp xp fp. Now we have to find out what is the kp. Kp in this case, so we have got this relation that a square is given by kp by k and xi p by xi. Now a is equal to also p pi by capital N. So from these two relation we can write down easily that kp by k into xi by xi p is p square pi square by n square. Now if we take kp on the left side and move everything to the right side, xi p by xi p square pi square by n square. Now we want to use the relation that xi p is, please see lecture to find out how this is derived. Xi p is 2n xi. So if you put that here, kp k into 2n into xi by xi p square pi square n square. So there will be one in cancellation and it will be 2k p square pi square by n. This is the kp. So the correct option in this case, the first one. So what is this a square? We got in the previous case this equation, this a square. So where is, so how to get that? So if you put, so we are trying to calculate what is the form of this term psi p ddt of xp. So for that we are replacing ddt of r and t from the equation we got earlier, and if we do integration by parts, so if you put back this here, this whole thing ddt, if you put back this here, then there will be two integration to do. If you do integration by parts, you will get something of the form like this equation, and from that you can calculate that there is equation of the form of this where a square is given by this. Okay. Next question. Question number 5, 6. In the Rouse model, relation between diffusivity and number of segments A. So d Rouse is proportional to 1 by n to the power mu. So in each option the left hand side is d Rouse 1 by n to the power mu minus 1, C proportional to 1 by n to the power mu plus 1, d is proportional to 1 by n. So each of these cases this is d Rouse. Now which of these is the correct option? To calculate that, so we have to calculate what is the image d of center of mass that will capture the diffusion constant of the polymer chain, right? So image d of the center of mass, so the image d of center of mass, because it captures the net diffusion of polymer chain. So suppose this is at time step some t1, this is time step t2, the center of mass is moving from here to here. This will give some idea about how much polymer is diffusing. So this is at times instant t1, this is at t2, so this will give some idea. So what we need to calculate, here RCM at time t minus RCM at t0, this whole square average. Now because there is times translation invariant, we are fixing one of the time points as 0, and at time t how much it has gone, the center of mass we want to calculate. So it will be alpha sum over xyz x0 alpha t minus x0 alpha 0 whole square average. Now we already know this particular relation, that the incidental average of x0 t minus x0 alpha component x0 t minus x0 beta component, this is given delta alpha beta 2 kt by sine naught into time. Now in this case, because alpha and beta is always equal, so this particular term will result in some term like 2 into 3, because there is 3 term like this x, y, z, 3 kt by xi 0 is n xi into t. So it is 6 kt by n xi into time. 6 kt by n xi into time. Now from the Einstein relation in 3D, we have discussed what is the relation of x square average in 3D, which is 6 dt. Now if we compare here, we got msd equal to 6 kbt by n xi into time. So comparing these two relations, we get d is equal to kbt by n xi kbt by n xi, diffusion constant equal to, and which says that d is proportional to 1 by n. But the important point here is only this is valid only for Rao's model. So it appears that this is not the exactly correct relation, because we haven't taken into account the hydrodynamic interaction, the interaction with the solvent molecules in the solution. We haven't taken into account those and the hydrodynamic interaction. So this diffusion constant is only approximate, uh, giving an approximate behavior with respect with in number of segments, which gives the idea that if the number of segments is large, so polymer is heavy, it will diffuse less, which is a common idea that if the objective is itself is heavier, then due to the thermal fluctuation it will not move much, the diffusion will not be that strong. Okay, now one more question from the same line. Question number 7. Question number 7 is the time correlation of end to end distance is captured by option A, zeroth Rao's mode, option B, odd Rao's mode, C, even Rao's mode, option D, first Rao's mode. So these are the options. Now how to calculate the time correlation between end to end distance? So end to end distance is given by end to end distance. This is given by RET is R of n comma t minus R of 0 comma t. So r of n comma t, capital N comma t is the location of the nth bit, capital nth bit. So one extremum of the bit chain, and r0 t is the another extremum of the chain. So if we take a vector difference between those two, that will be the end-to-end distance. Now from our all the calculation, we got that r of n comma t is given by x0 plus 2 into p1 to infinity xp cos of p pi small n by capital N. So if we want to calculate what is this r capital E, capital R end to end, so x0 will cancel, and there will be terms like 2, let me write down explicitly. So there will be one term something like 2 into p1 to infinity xp. Now if you put cos here, that will give you a minus, so it is, so cos of p pi, so that will be minus because p is integer. Sorry, xp cos of p pi minus 2 into sum over p 1 to infinity xp, and if you put n is equal to 0 here, that will be always 1. So this, so if we take common, 2 of p to infinity xp cos of p pi minus 1, which is like minus 4 into p odd xp. So if you understand it correctly, that if p is even, in that case this cos p pi will give you 1, that term will be 0, so there will be no contribution. But if p is odd, this cos p pi will be in a negative minus 1 quantity, and minus 1 is minus 2. If we take club these minus 2 and 2 together, that will give the input minus 4 in front, and sum will be only survive on p is equal to odd xp. So that is RET at some time. Now we want to calculate the time correlation between end-to-end distance. So RET, RE0, this quantity. So that will be 16 P odd XPT, comma XP0, and then this is already calculated somewhere in memory, that this quantity is given by 3 kBT by Kp e to the power minus t by tau p. Please check the calculation in the lectures, where tau p is given by tau 1 by p square. Now you can see, if so, this quantity is dependent on e to the power minus some factor into p square. So as p is increasing, p is equal to odd, so there is sum over. So there are other terms also, but I am only interested in what is the power of the exponential, because that will be the most dominating. P is only odd, so first p will be p is equal to 1, and the next will be p is equal to 9, which will give you exponential of minus 9, so which is like very small term. So the most contribution of this term will come from p is equal to 1. So that's why the time correlation between end-to-end distance is given by the first Rouse mode only, because after first Rouse mode, due to the exponential nature of uh, this correlation, the next terms will be exponential minus n, and then exponential minus 16, something like that. So it will be increasingly small and smaller, so contribution will be very small also. So we can say that the largest contribution is given by the first round monsoon. Okay, let us discuss next problem. So one question is there. I have already discussed this question, that Rao's model is, option is FJC model or bead spring model, option C Maxwell model, option D tube model. So basically we have discussed this. This is bead spring model, FJC is not. So there are bead, there are springs also. We are trying to see the what is the continuum version of that model, bead spring model basically. And tube model and Maxwell model we will learn later in the coming modules. Tube model is related to rotation of the polymer. FJC we have already discussed in the first section, where it is like freely jointed chain. There are no interaction at all between the segments of the polymer. Okay. One more, the mobility matrix. So in the last part of this module, mobility matrix is discussed. Mobility matrix. So the actual mobility matrix usage of that and the importance of that will come in the next module only. Here we have some introductory part only about the mobility matrix. So what it does, option A, so it's like mobility matrix relates, option A, velocity to force, option B, velocity to position, option C, displacement to distance, option D, solvent velocity to solute velocity. So the correct option here is velocity to force, because the mobility matrix is something like V of nth particle, velocity of nth particle is sum over m h n m f of m. This m matrix, h and m matrix, that is called the mobility matrix. Mobility matrix. So this is the force, this is the velocity. So there will be effect of, so force due to the nth particle is affecting the force of the nth particle. So it is connecting. So nm, so it is h and m is a matrix which connects all the forces by all the particles to velocity of the all particles. So this h and m is called the mobility matrix, which connects force to velocity to force. Okay. Okay, good. Any doubt? Okay, good then. We'll meet next week again with the next module. We'll discuss some problem from the next module. Okay, bye.